Welcome back everyone. So we are studying NPTEL course on topological phases of matter, and we are on the chapter for symmetry. Especially we are looking into discrete symmetry which play a role in giving you a topological phases, giving protection to the topological phases and Dirac cones, and as well as help us classify various topological phases or topological invariants. Okay. So we looked into the mainly three symmetries or three symmetries: inversion, time reversal and reflection. So reflection is something that we will not go in details, but we will give enough homework for you to work it out based on what we have learned about inversion symmetry and time reversal symmetry. So right now we are studying how the symmetries manifest in various states in both position space and momentum space. And in the last class we showed that if I have an abstract state under inversion, it changes this way. Now in the position space it changes at, if the state was defined at x, it will change to minus x. X here stands for a 3 dimension or odd dimension. Okay. So x1, x2, x3, all these things. So in this derivation we said that either you can put the inversion in the variable in the wave function or in the state. So let me go back and show how this is done. Okay. So let me rederive it. Okay. So I want inversion acting on some state, and the state was, let us do it for momentum, and then it will be the same in the position space. So the state is expanded in this basis, which was that giving a resolution operator in the momentum space, right. So identity is what we have inserted. P psi and then once we put inversion, so now we can do it in two ways. Either we can apply the inversion on this state and this one just remains as the wave function in the momentum space, or one can even start with the state and then we can put the resolution operator later. So let us do it two ways. So in this way it will be like this, and then this is just a number, it goes like this, and this one is goes to minus p by definition, as momentum goes to minus momentum under inversion, and then we make p goes to minus p, measure remains same. Okay. So this and this, if we compare, then this is how the state will change. The other way is first you put the inversion operator on the state, then we put the resolution operator. Okay. So, now this one inversion acts on P and gives us psi. Okay, one more step, gives us minus P psi, that is equal to psi minus P is equal to psi minus P. So, in both ways we get psi P changes to, under inversion, changes to psi minus P. And if you follow the same step here, which I did it in this way, which is also equivalent, okay, but I just wanted to show you these three ways of doing it. You can also put it in the manifold, because these are in the base manifold, right, where the symmetry is acting. And if you do the other way, which I have just showed it for the momentum case, you will also obtain the same result. Okay. So, then we also talked about the time reversal, and under time reversal things will also go the same way. So, let me just summarize what we have done. Under inversion, psi x goes to psi minus x, psi p goes to psi minus p, and under time reversal psi x goes to psi star x, psi p goes to psi star minus p, and with reflection one can do the same thing. Okay. So, why they are important is the fact that now go back to the Berry curvature for a given band, okay, as a function of momentum p equal to hk. So, we usually do it in terms of wave vector, but it will be the same thing. So, show that. So, this will be homework for you. It is very easy to show based on these results. If change to or minus f k. So, the Berry curvature for the same band becomes at k and minus k become equal if you have inversion symmetry, and if you have time reversal symmetry, k would goes to minus k and you will get a negative sign. So, now if I have inversion plus time reversal, do it twice, equal to minus f mu nu, k changes to minus k under inversion and then again change to minus k to plus k under time reversal. So, f is equal to minus f at every k point, which means it is 0. So, this is an important result. So, the Berry curvature is identically 0 if you have both inversion and time reversal symmetry. So, that is why one of the symmetry must be broken to get a finite Berry curvature and finite Chern insulator. We will show that all those Chern insulator that we looked into earlier, which is Holden model, Rice-Miller model, they break time reversal symmetry. So, time reversal symmetry breaking is an important criteria for the Chern number to appear. Okay. It requires time reversal to be broken. Okay. So, I have completed the symmetry representation in first quantization. Now we will go to second quantization. Because all our Hamiltonians are in second quantization, so we will take examples in second once we complete the second quantizations one. Okay. So we briefly introduced what is second quantization, and we will do that again, the necessary ones. But let me just give you the punchline. In whichever, either in real space or momentum space, we will have a Hamiltonian written, let us say, in some spatial coordinate I and j, and between orbitals or spin alpha and beta, like orbitals or spins or sublattice and so on, and these are the spatial. And you can go to the momentum space. This is roughly the Hamiltonian would look like if I do not specify anything else. So, it is a hopping from I to j, and assuming that the hopping is spatial independent, so because of the translation and invariance, and then between same orbital and different orbital or spin and so on. So, this is the Hamiltonian, and in the momentum space that will look like okay. So, now in the second quantization we seem to have two Hamiltonian to look into, and this is where the things will getting interesting. One is, this is the Hamiltonian, this is the actual Hamiltonian, and then we have a matrix element of the Hamiltonian in real space or in momentum space, and which is a matrix in the orbital basis and localized at given k points. So, all the symmetry operators that commutes with this Hamiltonian, but with this Hamiltonian it may not simply just commute, it can change k to minus k, and sometimes it will also anti-commute, and then sometimes also you will get a h star, small h star or transpose and so on and so forth. So, on the symmetry we do not need this second quantized Hamiltonian to commute anymore, but it will always commute with this. That is the definition of symmetry. And the second point I wanted to make is that now this is an operator. Now it sort of seems to be broken into three operators, which are creation and annihilation operator, and you also have the matrix elements. So, do an operators as a matrix in the matrix form transform as the operator transforms, with the symmetry operator being O, H, O inverse, whereas a state only transformed by just the symmetry operator O. But now we are writing those states in an operator form. How are they going to transform? Are they going to transform like an operator or like a state? This is a common confusion, at least in the initial state, and let me show you whether you write it in a operator way or not. It should always transform like a state, because these are actually acting on some, they are operator in some Fock state. They are not an operator in the Hilbert space, and Hilbert space is defined in terms of this basis, and it is carrying only one index. So, if a quantity that carries one index you just need one operator acting on that index to give you another index. So it would transform like a state. Whereas here the matrix element of the Hamiltonian has two indices, so they will transform like the operator. Okay. So let me now show it slightly more explicitly, but we will not be in a microscopic details of this derivation, but it should be very obvious. So C and C dagger are operators in the Fock space of some number operator, and we are in the fermionic case, so the number operator takes only two values 0 and 1, and the corresponding states are empty state or vacuum and one fermion. Right now I am not considering spin. If I have spin, then you can generalize to two spins, right. In our Hilbert space, the way we talk about, and one more thing, 1 is defined by C dagger 0. Okay. So it's actually an operator acting on kind of a ladder operator. So it acting on one Fock state give you another Fock state. So it's an operator only defined in the Fock state. Okay. So however, our Hilbert space that we need to worry about are in some lattice that I have some ith site and j site. So I have some local site, and at each site I can have orbitals, more than one orbital, which is indexed by alpha, and I can also have electrons being spin up and down. Okay, and alpha can take a number of orbitals if you choose. So that means I have a state at site I with alpha and sigma, and this state I can even combine to make it look simpler, is called I, which includes both space coordinate and the internal degrees of freedom together, and that state is defined by creating an electron at that site, at this orbital, at this spin from vacuum. So it still has only one index I. So now let us say I have some symmetry operator. I want to see how state transform. Okay, and I transform to some I prime state. So I have ace and I have C dagger I 0. So one can stop here and do this, that I will have, okay, so it goes from I j c, or let me do it this way. and that I can call at C prime operator. So you can see you get a new creation operator at J, and J consists of all the indices, and that depends on the symmetry. If the symmetry changes from site I to J under some inversion, then it will, but then it does not do anything for the orbital and spin. So it will just act on this state and won't change these things. So it will just take I2, small I2 minus I. Or if I have for example time reversal symmetry for spin half, so it will take an up spin to down spin at the same side I. So that is what I to J transformations will, and we will take example today to show that. So this is kind of a creation operator at an index J, which we obtained from the symmetry transformation, and this will be a matrix that we have to construct based on here I have I index summed over. So you can see that it essentially operationally act like this. But now one can say that, well, I can also, and it's kind of a choice. I can also introduce S inverse S equal to identity, and then you will have S inverse S. Okay. So now let's do that here. Equal to, or let me keep the vacuum. So we have S, C I, dagger, S inverse, S 0, and the vacuum does not change under any symmetry, especially the vacuum that we are talking about, which is truly a vacuum, not a many body ground state, which is often taken as a vacuum for some excitations, and that sort of vacuum are different because they can have different symmetry. But here the vacuum we are talking about is a vacuum which is a truly no particle, and under any symmetry it just remains vacuum. So this remains. So then this is the transformation. Okay, and right now J I S I. So you can see that we can still write it as an operator, Cj prime dagger is equal to, or even if I remove the index, index will be absorbed into this. S C dagger is prime, but operationally it still acts like this. Which is just with one S I J C I J. Okay. So this is the important part. And then if you do the same thing about the annihilation operator, then it will be the other way. Okay. So, for the creation operator, if you define the symmetry to be on the left hand side, for the annihilation operator it will be from the right hand side with a stagger. Okay. So, let me just remind you again what we said. Although C and C dagger are called operator, they transform as vector because they represent state. Then often we, as we go to different real space to momentum space, the transformation is going to only act on the spatial coordinate, not on the internal coordinate. So, let me break it down to this I we defined as I, alpha and sigma, right. So, at every site I have n number of orbitals, alpha runs from 1 to n, and spin. So, that means the state can actually be written as a direct product of all the positions and then all the orbitals and all the spins, right. So, which means the symmetry operator that acts on this entire Hilbert space can also be then split into an operator that act on this I and an operator that act on the orbital if at every site if the symmetry changes different orbital, and also spin keeping the same orbital at the same site if the symmetry, for example spin rotational symmetry or time reversal symmetry, if that changes spin, then you can also write it this way. Okay. And I to j would correspond to ij going from I side to j side, alpha to beta, and sigma to sigma prime. So, writing it explicitly, j beta sigma prime s. Okay. I change the now index from j to I and I to j. So, I j v alpha beta r sigma sigma prime c dagger j beta sigma prime. Okay. So, you can look into each one separately and get a better idea about how things changes. So, now in momentum space, or Fourier space. So, C in Fourier space I alpha sigma okay, and Ci alpha sigma will be So, then in the Fourier space Ck under a given symmetry, how it is going to change? Alpha sigma was equal to Uij V alpha beta R sigma sigma prime Cj beta sigma prime is the transformation. So, now let us do the Fourier transformation of this guy. So, I will put 1 over n k j beta sigma So, I can actually split all the Fourier transformation this way. And then you will have beta and sigma okay. So, it looks like and this is equal to, if I do the Fourier transformation of this, this is J K alpha sigma. So, it does look like that I just have to compare this with this and this with this, and how do they transform. But one thing we have to be careful, once we see how a R position changes to Rj, how Ri and Rj are related to each other by a given symmetry, that would actually change whether you are still stick to the same k point or not, and that will manifest into, under this symmetry transformation, C here it is a prime, whether C prime k is related to Ck for the different orbital and spin, that depends on the symmetry of these two guys. But in the k point, whether they remain in the same k point or not, that will depend on this. So, they appear to look to be completely separated, but you will see that they will be related to each other, and that we can see it through example. Let us take the example of inversion. Which is to say Ri goes to minus Ri, that is my Rj, right. And whereas alpha, which is supposed to go to beta, does not change, and sigma goes to sigma prime equal to sigma. So, which gives us V equal to identity. In the orbital space, V does not do anything, and in the spin space, this is also identity, it does not change the spin. This one, if you make these things as a vector, there will be a version for U that will, then you can write a matrix for that, which we did in one of the earlier class. But here what we will do is that we will just by hand we will put this thing. Okay. So, under inversion then so Rj just go to Ri, right, or let me do it step by step. I k Rj is equal to minus Ri and then I equal to j. So, it becomes e to the power minus I k R I, which we can write as minus k dot R I. So, and then C I alpha sigma let us do this one. So, this becomes equal to now minus I or plus I minus k dot R j, and there is a summation over k. So, let us write this entire thing. So, j summation is gone and alpha beta summations are also gone because these operators are identity, it does not change the orbital or anything. So, you will have C I C k alpha sigma. Now, what we can do is that we can change k to minus k. So, then we will have 1 over square root of n k e to the power, I change k to minus k. So, I will get e to the power I k dot R I C minus k alpha sigma, and this one was compared to this gives us changes to C minus k alpha sigma under inversion. So, whereas in real space so in real space also under inversion it changes from a state that was localized at the ith site to a position that is minus r. So, all the positions coordinates were changed to minus r, right, whereas orbital and spin remain same. In the momentum space, that corresponds to a wave vector k to minus k under inversion. Time reversal. So, under time reversal R I remains R goes to Rj, which is equal to Ri. In real space we do not do any changes, and orbital goes to the same orbital so U being identity, V being identity. Let us not worry about the spin, ignore spin for the time being. Let us do it for a spinless case first. But now recall the fact that it still has, so U, V, but a complex conjugation is there, which is equal to identity, identity equal to just complex conjugation. Now if you do that, I alpha is equal to so under now time reversal, whether I put it in one side or two sides, it does not matter, it just acts on this. So now this is the one, so everybody else remains same, I remains to I, Ri remains to Ri, and alpha remains to alpha, so nothing changes, so it becomes e to the power, however I goes to minus I, where k remains to k and Ri remains at Ri, and Ck alpha. But you see, again we are getting a negative sign. So again we can change k to minus k. So we take this one and put it here, which is equivalent to C minus k alpha. Okay. So now under time reversal also, Ck alpha goes to C minus k alpha under time reversal. So it again changes k to minus k, but the thing about time reversal and inversion is that here also k goes to minus k, but in both cases k goes to minus k, but for a different reason. In one case, because Ri changed to minus Ri, which is equivalent to changing k to minus k in the momentum space. In the second case, it was I goes to minus I, which is equivalent to changing k to minus k. And one more thing can be a potential confusion is that when time reversal is acting on this operator, there might be a tendency to make C goes to C dagger goes to C because of the complex conjugation, but that is physically not correct, because K is a complex conjugation operator that acts on the any sort of a I, but this one C and C dagger, they are complex conjugate to each other in the sense that they one of them is kind of a destroying a particle, another is creating a particle. So they are not complex conjugate to each other in the complex analysis sense. It was just a kind of a different operator form, and both are however real in the matrix representations of the Fock space of 0 and 1. So, under complex conjugation, C dagger won't change to C. A creation operator remains a creation operator. Okay. So, this is something that you can keep in mind. So, it remains C dagger remains C dagger. Now, if I have spin, obviously we have already talked about under time reversal, it will go to C minus k down and C k down will go to C minus k up, but with the negative sign. So, t square equal to minus 1. Here t square equal to plus 1. Here t square equal to minus 1. Alright, so we stop here today. We talked about how the operators will look like in second quantizations. In the next class, we will see how the second quantized Hamiltonian will look like, will transform under these symmetries. Thank you very much for your attention.